Exiting the solar system isn't easy. You must escape the Earth's and Sun's combined gravitational pulls. Of all the spacecraft ever launched, only 5 are on solar system departing trajectories. The first, Pioneer 10, was launched a half-century ago. Humanity's first spacecraft to encounter Jupiter, that gravitational assist accelerated it beyond escape velocity. It remained our most distant probe until 1998, when Voyager 1 overtook it. Launched 46 years ago, the Voyager 1 and its twin are time capsules of their era in many ways. They captured the public imagination in the 1970s and 80s as Earth's first ambassadors to the outer planets, providing close-up images of Jupiter, Saturn, Uranus, and Neptune. In recent decades, despite their now archaic memory and transmission systems, the Voyagers remain on the cutting edge of space exploration as the only instruments to ever travel through interstellar space. However, space, as we know, is always harsh. As a result, there's something terrifying is happening on board one of the most iconic NASA spacecraft of the 20th century. Voyager 1 has just stopped communicating with Earth. What happened? Did Voyager just make contact with an unknown force in interstellar space? Or is it simply a 46-plus-year-old machine that is malfunctioning? Join us as we dig deep into the real reason behind Voyager 1's glitch.
The Voyager spacecraft are bound for the stars. They're on escape trajectories from the solar system, barreling along at almost 1 million miles a day.
If the stars hadn't aligned, 2 of the most remarkable spacecraft ever launched never would have gotten off the ground. In this case, the stars were actually planets, the 4 largest in the solar system. Some 60 years ago, they were slowly wheeling into an array that had last occurred during the presidency of Thomas Jefferson in the early years of the 19th century. For a while, the rare planetary set piece unfolded largely unnoticed. The first person to call attention to it was an aeronautics doctoral student at the California Institute of Technology named Gary Flandro. It was 1965, and the era of space exploration was barely underway. The Soviet Union had launched Sputnik 1, the first artificial satellite, only 8 years earlier. Flandro, who was working part-time at NASA's Jet Propulsion Laboratory in Pasadena, Calif, had been tasked with finding the most efficient way to send a space probe to Jupiter, or perhaps even out to Saturn, Uranus, or Neptune. Using a favorite precision tool of 20th century engineers, a pencil, he charted the orbital paths of those giant planets and discovered something intriguing. In the late 1970s and early 1980s, all 4 would be strung like pearls on a celestial necklace in a long arc with Earth. This coincidence meant that a space vehicle could get a speed boost from the gravitational pull of each giant planet it passed, as if being tugged along by an invisible cord that snapped at the last second, flinging the probe on its way. Flandro calculated that the repeated gravity assists, as they are called, would cut the flight time between Earth and Neptune from 30 years to 12. There was just one catch. The alignment happened only once every 176 years. To reach the planets while the lineup lasted, a spacecraft would have to be launched by the mid-1970s. As it turned out, NASA would build 2 space vehicles to take advantage of that once in more than a lifetime opportunity. Voyager 1 and Voyager 2, identical in every detail, were launched within 15 days of each other in the summer of 1977. After nearly 46 years in space, they are still functioning, sending data back to Earth every day from beyond the solar system's most distant known planets. They have traveled farther and lasted longer than any other spacecraft in history, and they have crossed into interstellar space, according to our best understanding of the boundary between the Sun's sphere of influence and the rest of the galaxy. They are the first human-made objects to do so, a distinction they will hold for at least another few decades. What an unparalleled and unexcelled record, especially when we consider that the Voyager missions were originally planned to last just 4 years. Early in their travels, 4 decades ago, the Voyagers gave astonished researchers the first close-up views of the moons of Jupiter and Saturn, revealing the existence of active volcanoes and fissured ice fields on worlds astronomers had thought would be as inert and crater-pocked as our own moon. Specifically, Voyager 1 reached Jupiter in March 1979, 546 days after its launch. Voyager 2, following a different trajectory, arrived in July of that year. Both spacecraft were designed to be stable platforms for their Vidicon cameras, which used red, green, and blue filters to produce full-color images. They hardly spin at all as they speed through space. Their rotational motion is more than 15 times slower than the crawl of a clock's hour hand, minimizing the risk of blurred images. Altogether, the Voyagers took more than 33,000 photographs of Jupiter and its satellites. It felt like every image brought a new discovery. Jupiter had rings. Europa, one of Jupiter's 53 named moons, was covered with a cracked, icy crust, now estimated to be more than 60 miles thick. As the spacecraft left the Jupiter system, they got a farewell kick of 35,700 miles per hour from a gravity assist. Without it, they would not have been able to overcome the gravitational pull of the Sun and reach interstellar space. At Saturn, the Voyagers parted company. Voyager 1 hurtled through Saturn's rings, taking thousands of hits from dust grains, flew past Titan, a moon shrouded in orange smog, and then headed north out of the plane of the planets. Voyager 2 continued alone to Uranus and Neptune. In 1986, Voyager 2 found 10 new moons around Uranus and added the planet to the growing list of ringed worlds. Just 4 days after Voyager 2's closest approach to Uranus, however, its discoveries were overshadowed when the Space Shuttle Challenger exploded shortly after launch. All 7 of Challenger's crew members were killed, including Krista McAuliffe, a high school teacher from New Hampshire who would have been the first civilian to travel into space. 3 years later, passing about 2,180 miles above Neptune's azure methane atmosphere, Voyager 2 measured the highest wind speeds of any planet in the solar system, up to 1,000 miles per hour. Neptune's largest moon, Triton, was found to be one of the coldest places in the solar system, with a surface temperature of minus 391 degrees Fahrenheit or minus 235 degrees Celsius. Ice volcanoes on the moon spewed nitrogen gas and powdery particles 5 miles into its atmosphere. Voyager 2's images of Neptune and its moons would have been the last taken by either of the spacecraft had it not been for astronomer Carl Sagan, who was a member of the mission's imaging team. With the grand tour officially completed, NASA planned to turn off the cameras on both probes. Although the mission had been extended with the hope that the Voyagers would make it to interstellar space, it had been officially renamed the Voyager Interstellar Mission. There would be no photo ops after Neptune, only the endless void and impossibly distant stars. Sagan urged NASA officials to have Voyager 1 transmit one last series of images. So, on Valentine's Day in 1990, the probe aimed its cameras back toward the inner solar system and took 60 final shots. The most haunting of them all, made famous by Sagan as the pale blue dot, captured Earth from a distance of 3.8 billion miles. It remains the most distant portrait of our planet ever taken, veiled by wan sunlight that reflected off the camera's optics. Earth is barely visible in the image. It doesn't occupy even a full pixel. Sagan, who died in 1996, worked really hard to convince NASA that it was worth looking back at ourselves, Spilker says, and seeing just how tiny that pale blue dot was. The tenacity and commitment of astronomers like Sagan were rewarded on August 25, 2012, when Voyager 1 passed through the heliopause that marks the edge of the Sun's solar wind and entered interstellar space. In 2018, Voyager 2 did so as well. Now, the 2 spacecraft are chugging through the vast outer reaches of the solar system. They continue to send signals back to Earth, updating humans about their adventures far beyond the planets. In other words, the Voyagers were beyond astronomers' wildest dreams. But we know that their unexpectedly lengthy journeys have not been without challenges. Voyager 1 has 3 onboard computers, including a flight data system that collects information from the spacecraft's science instruments and bundles it with engineering data that reflects the current health status of Voyager 1. Mission Control on Earth receives that data in binary code, or a series of ones and zeros. But Voyager 1's flight data system now appears to be stuck on auto-repeat, in a scenario reminiscent of the film Groundhog Day. The mission team first noticed the issue November 14th, when the flight data system's telecommunications unit began sending back a repeating pattern of ones and zeros, like it was trapped in a loop. While the spacecraft can still receive and carry out commands transmitted from the mission team, a problem with that telecommunications unit means no science or engineering data from Voyager 1 is being returned to Earth. According to NASA, the Voyager team sent commands over the weekend for the spacecraft to restart the flight data system, but no usable data has come back yet. NASA engineers are currently trying to gather more information about the underlying cause of the issue before determining the next steps to possibly correct it. Media relations specialist at NASA's Jet Propulsion Laboratory in Pasadena, California, which manages the mission. The process could take weeks. The last time Voyager 1 experienced a similar but not identical issue with the flight data system was in 1981, and the current problem does not appear to be connected to other glitches the spacecraft has experienced in recent years. As both Voyager probes experience new trials, mission team members have only the original manuals written decades ago to consult, and those couldn't account for the challenges the spacecraft are facing as they age. The Voyager team wants to consider all of the potential implications before sending more commands to the spacecraft to make sure its operations aren't impacted in an unexpected way. Voyager 1 is so far away that it takes 22.5 hours for commands sent from Earth to reach the spacecraft. Additionally, the team must wait 45 hours to receive a response. As the aging twin Voyager probes continue exploring the cosmos, the team has slowly turned off instruments on these senior citizens to conserve power and extend their missions. Along the way, both spacecraft have encountered unexpected issues and dropouts, including a 7-month period in 2020 when Voyager 2 couldn't communicate with Earth. In August, the mission team used a long-shot shout technique to restore communications with Voyager 2 after a command inadvertently oriented the spacecraft's antenna in the wrong direction. While the team hopes to restore the regular stream of data sent back by Voyager 1, the mission's main value lies in its long duration, Cofield said. For example, scientists want to see how particles and magnetic fields change as the probes fly farther away from the heliosphere. But that dataset will be incomplete if Voyager 1 can't return information as it continues on. The mission team has been creative with its strategies for extending the power supply on both spacecraft in recent years to allow their record-breaking missions to continue. As Cofield said, the Voyagers are performing far, far past their prime missions and longer than any other spacecraft in history. So while the engineering team is working hard to keep them alive, we also fully expect issues to arise. Otherwise, we know that although the spacecraft are both running low on power, their journeys are far from over. Indeed, we're talking about the engraved golden records strapped to NASA's twin Voyager spacecraft, which have passed into interstellar space. Although the spacecraft will likely fall silent in a few years, the records will remain. Nick Oberg, a doctoral candidate at the Kaptein Astronomical Institute in the Netherlands, and a colleague wanted to calculate which, if any, stars the two Voyager spacecraft may encounter in the long future of our galaxy. But the models let them forecast much, much farther into the future. Oberg presented their work at the 237th meeting of the American Astronomical Society, held virtually due to the coronavirus pandemic, on Jandausor 12, where he spun a tale of the long future of the twin Voyagers and their golden records. Oberg and his colleague combined tracking the Voyager's trajectories forward with studying the environments the spacecraft will fly through to estimate the odds of the golden record surviving their adventures while remaining legible. The result is a forecast that stretches beyond not just humanity's likely extinction, but also beyond the collision of the Milky Way with the neighboring Andromeda galaxy, beyond even the extinction of most stars. The new research was inspired by the release of the second batch of data from the European Space Agency's spacecraft Gaia, which specializes in mapping more than 1 billion stars super precisely. But I warn you, don't get excited for any upcoming milestones. Not until about 20,000 years from now will the Voyagers pass through the Oort cloud, the shell of comets and icy rubble that orbits the Sun at a distance of up to 100,000 astronomical units, or 100,000 times the average Earth-Sun distance, finally waving goodbye to its solar system of origin. As Oberg said, at that point for the first time, the craft will begin to feel the gravitational pull of other stars more strongly than that of our own Sun. It's another 10,000 years before the spacecraft actually come near an alien star, specifically a red dwarf star called Ross 248. That flyby will occur about 30,000 years from now, although it might be a stretch to say that the spacecraft will pass by that star. According to Oberg, it's actually more like Ross 248, shooting past the nearly stationary Voyagers. By 500 million years from now, the solar system and the Voyagers alike will complete a full orbit through the Milky Way. There's no way to predict what will have happened on Earth's surface by then, but it's a time span on the scale of the formation and destruction of Pangaea and other supercontinents. Throughout this galactic orbit, the Voyager spacecraft will oscillate up and down, with Voyager 1 doing so more dramatically than its twin. According to these models, Voyager 1 will travel so far above the main disk of the galaxy that it will see stars at just half the density, as we do. The same difference in vertical motion will also shape the differing odds each spacecraft's golden record has of survival. The records were designed to last, meant to survive perhaps 1 billion years in space. Beneath the golden sheen is a protective aluminum casing, and below that, the engraved copper discs themselves. But to truly understand how long these objects may survive, you have to know what conditions they'll experience, and that means knowing where they will be. Specifically, Oberg and his colleague needed to know how much time the spacecraft would spend swathed in the Milky Way's vast clouds of interstellar dust, which he called one of the few phenomena that could actually act to damage the spacecraft. It's a grim scenario, dust pounding into the Voyagers at a speed of a few miles or kilometers per second. The grains will act as a steady rain that slowly chips away at the skin of the spacecraft. A dust grain only 1,000th of a millimeter across will still leave a small vaporized crater when it impacts. Voyager 1's vertical oscillations mean that spacecraft will spend more time above and below the plane of the galaxy, where the clouds are thickest. Oberg and his colleague simulated thousands of times over the paths of the two spacecraft and their encounters with the dust clouds, modeling the damage the golden records would incur along the way. That work also requires taking into consideration the possibility that a cloud's gravity might tug at one of the Voyager's trajectories. As Oberg explained, the clouds have so much mass concentrated in one place that they actually may act to bend the trajectory of the spacecraft and fling them into new orbits, sometimes much farther out, sometimes even deeper, toward the galactic core. Both golden records have good odds of remaining legible, since their engraved sides are tucked away against the spacecraft bodies. The outer surface of Voyager 1's record is more likely to erode away, but the information on Voyager 2's record is more likely to become illegible. The main reason for this is because the orbit that Voyager 2 is flung into is more chaotic and it's significantly more difficult to predict with any certainty of exactly what sort of environment it's going to be flying through. But despite the onslaught and potential detours according to Oberg predicted, both golden records are highly likely to survive at least partially intact for a span of over 5 billion years. After those 5 billion years, modeling is tricky. That's when the Milky Way is due to collide with its massive neighbor, the Andromeda Galaxy, and things get messy. The orderly spiral shape will be severely warped and possibly destroyed entirely. The Voyagers will be caught up in the merger, with the details difficult to predict so far in advance. Meanwhile, the vicarious sightseeing continues. Oberg and his colleague calculated that in this 5 billion year model-friendly period, each of the Voyagers likely visits a star besides our Sun within about 150 times the distance between Earth and the Sun, or 3 times the distance between the Sun and Pluto at the dwarf planet's most distant point. Precisely which star that might be, however, is tricky. It may not even be a star we know today. While neither Voyager is likely to get particularly close to any star before the galaxies collide, the craft are likely to at least pass through the outskirts of some star system, Oberg said. The very strange part is that actually might be a system that does not yet exist, of a star that has yet to be born. Such are the perils of working on a scale of billions of years. From here, the Voyager's fate depends on the conditions of the galactic merger. The collision itself might kick a spacecraft out of the newly monstrous galaxy, a 1 in 5 chance, although it would remain stuck in the neighborhood. If that occurs, the biggest threat to the golden records would become collisions with high-energy cosmic rays and the odd molecule of hot gas. These impacts would be rarer than the dust that characterized their damage inside the Milky Way. Inside the combined galaxy, the Voyager's fate would depend on how much dust is left behind by the merger. Oberg said that may well be minimal, as star formation and explosion both slow, reducing the amount of dust flung into the galaxy. Depending on their luck with this dust, the Voyagers may be able to ride out trillions of years, long enough to cruise through a truly alien cosmos. He concluded that such a distant time is far beyond the point where stars have exhausted their fuel and star formation has ceased in its entirety in the universe. The Voyagers will be drifting through what would be, to us, a completely unrecognizable galaxy, free of so-called main-sequence stars, populated almost exclusively by black holes and stellar remnants such as white dwarfs and neutron stars. And it's a dark future. The only source of significant illumination in this epoch will be supernovas that results from the once-in-a-trillion-year collision between these stellar remnants that still populate the galaxy. Our work, found on these records, thus may bear witness to these isolated flashes in the dark. However, as a piece of good news, NASA finally is getting serious about an interstellar mission. The researchers have a vision for a mission that could be built with existing technology. Indeed, the group says that if their mission is selected by NASA, it could fly as soon as 2030. This is humanity's first explicit step into interstellar space, says Pontus Brandt, a physicist at the Johns Hopkins Applied Physics Laboratory who is working on the interstellar probe study. The basic idea for the interstellar mission is to launch a spacecraft weighing less than 1,700 pounds on NASA's massive Space Launch System rocket, which is expected to be ready by 2021. That will get it traveling across our solar system like any other probe. To give it another boost, it will then use a gravity assist to sling the craft to speeds well over 100,000 miles per hour. The team at the Applied Physics Lab is currently considering 2 types of gravity assists: a plain vanilla assist that swings the probe around Jupiter, and another that swings it around the Sun. Using the Sun is advantageous because the spacecraft can reach far higher speeds than it can from a Jupiter assist. But the spacecraft would have to pass several times closer to the Sun than the Parker Solar Probe, which recently became the closest human-made object to pass by the star. This requires some serious heat shielding, but at a certain point, the heat shield becomes so bulky that it reduces the spacecraft's speed the closer it gets to the sun. The task for Brandt and his colleagues will be to find the sweet spot that takes the craft to interstellar space as fast as possible. Notably, NASA's new interstellar probe wouldn't just be looking backward to snap selfies of our cosmological home. It could also sample the zodiacal cloud, a mysterious ring of dust that extends to the outer region of the heliosphere and holds clues to the formation of our solar system. Traveling beyond this dust cloud will also give the spacecraft access to infrared light from the earliest galaxies in the universe that is otherwise blocked. And although it's impossible to know just what an interstellar probe might find out there, a dedicated mission beyond the solar system would drastically alter our understanding of the universe and our place in it, and it's really worth waiting. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.